Okay, so what we did last time is starting to analyze the divisor of GM minus GN. Let me just remind you. Um, so we denote NP to be some pair of functions, GN, GNP, 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 HNP. And we want to analyze GN and eventually HN in order to understand n torsion points. So we had a theorem. I mean, we started to talk about the theorem that says that for m greater than n, with m n m plus n and m minus n prime to the characteristic of the field, any elliptic curve E over K satisfies the divisor of GM minus GN is the divisor generated by m plus n torsion points. Namely, you take each m plus n torsion point and consider the divisor in which the sum of all these points, each of them with coefficient 1. You do the same for the m minus n torsion points. And you subtract the divisor generated by EM, well, twice the divisor, and twice the divisor generated by EN. Okay, and this is a big theorem. I mean, basically, almost everything we want to know about torsion points would follow from that. And in order to prove the theorem, there are several cases. What is going to happen is, you see, one way to prove this theorem is that we can say, I mean, I want to know what is the degree of GM minus GN, or rather the not the degree, the order of GM minus GN in each of the points. If I show that for any point P, the order of GM minus GN at P is the same as the the sum of the relevant coefficients, then I've shown. I guess I can do. I can write sum of. So it's enough to show that for any p, the order of gm minus gn at p is the sum of degrees in the right hand side. Okay, and in order to do this, we will divide the set of all points on the curve into 3 cases, and we show that in each of the cases this is what happened. So several cases. Case 1, we basically did. Case 1 is the points P in the intersection of EM and EN. Here, what we did is showing, we showed that, of course, the point at infinity is one such, it belongs to this intersection. And we showed that at O, Gm minus Gn has order -2. This was, I mean, essentially, it's because we know that both Gm and Gn have poles of multiplicity 2 at O, and they have different leading coefficients. And different leading coefficients. Namely 1 over m square and 1 over n square. And so the poles don't cancel each other. Now, we had a lemma that says that we can know. So if we take 2 points on the curve, and and a uniformizer at one of these points, say P. Then, if I look at the translation, TQ from E to E, rather from rational points, sorry, rational functions on E, rational functions on E, which takes a function R and sends it to R of I can write it like this, but maybe it's better. TQ of R, and TQ of R takes a point P and sends it to R of P plus Q. And we have this translation by Q within the argument of the rational function, and we showed that TQ of U, I mean U is a uniformizer, and if I apply TQ of U, then TQ on U, then this is a uniformizer at P minus Q. Now, using this lemma and the fact that we know that Gm minus Gn is has order -2 at O, I can conclude that it has order -2 at all points in the intersection. And this, we also talked about it, but it's not hard to see. Basically, if P is an n-torsion point, then Tp of Gn is simply Gn, because I mean you take Tp of Gn. Well, it's because n times P plus Q for any Q is going to be simply NQ, because P is an n-torsion point. So what I'm saying is, let's see. Yes, so if I want to calculate the order of Gn at P, then I might as well. So, I mean, I want to express it in terms of the order of Gn at O. But this is not, so this I know to be -2. And I claim that by the lemma we have this equality with the question mark above it. And the reason is if you take some uniformizer, so Gn is equal to u to the -2 times times s, where s is finite and non-zero at O, then I can simply apply TP on U, and this I know to be a uniformizer at P minus O is P. Hence, I can write Gn as TP U minus 2 times TPS S, and TPS evaluated at P is simply S at should be S at O. Yes, simply S at O, which we know to be different than 0 and infinity. So I get that I can express Gn also as a uniformizer to the power of -2 at P. So we get this orange equality. So that's something we talked about. I'm just sketching what we did, but the conclusion is that Gm minus Gn has order -2 at all of these green points. Any question about this part?
Thanks a lot for the overview. It has been very helpful.
Okay, so now we go to the other case. This case is points that are in EM but not in En. Now here it's also quite easy. These are not in either EM plus N nor in EM minus N. To see this, it's very easy. Like if P is not in, I mean, P is in EM and not in En, it means that NP is different than 0, and MP is 0. So obviously, M plus NP is different than 0. So it's not in EM plus En, but also M minus NP is different than 0. Okay, so we have this is this is an easy case because we can pin exactly where the point is. It's basically only in EM and not in the other components of the divisor. Now I claim, okay, so what do we need to show? That GM minus GN has order -2 at P. And this -2 again comes from just looking at the divisor, right? We take the blue divisor. And in this blue divisor, P appears only in EM, and it does not appear in any of the other components, right? So the coefficient of P is -2 in the divisor. Hence, we need to show that the left-hand side, namely the divisor of GM minus GN, has, I mean, we need to show that GM minus GN has order -2 at such points P. Now, we saw okay, so we saw that GM has order -2 at any point in EM. This was a basic lemma. And sorry, I need to take a look at something outside. Hey, sorry, there was some drama outside. Okay, so we want to show that GM minus GN has order -2 at these points P. And we already, so we know that GM has order -2. So this means that I can write GM as some uniformizer to the -2 times S, with S at P not 0 and not infinity. But now I can do like simple manipulation for GM minus GN. I write GM as I know, u minus 2 times s. And Gn I write as u minus 2 times u to the 2 times Gn. And now I take a u minus 2 factor, common factor, and I get s minus u2 Gn. So in order to show that Gn minus Gn has order minus 2 at P, it's enough to show that this guy does not vanish and is not equal to infinity at P. But if we check what it is, in S minus U square Gn at P is S at P minus basically minus 0, because U vanishes at P, and Gn of P is not 0. So it's I can write it as a multiplication U square of P times Gn of P And the reason I can write this multiplication is because I know that this is not 0. I mean, we assume that P is not an n-torsion point, and I know that this is 0. We had a lemma that if you want to evaluate a product of rational functions at a point, and you know that both values of the rational function at the point are finite, then you can just take the product of the evaluations. So all in all, this is simply S of P, which we know is different than 0 and infinity. Yes.
Why do we want to be sure that it can't be 0 multiplied by 0?
0 multiplied by 0 is okay, but we don't want Gn of P to be infinity.
Right. Right.
0 and I mean, this is like a general rule of thumb in analysis and other places. We can do finite non-zero times infinity. This usually makes sense. Infinity times infinity also usually makes sense. But the hard part is, I mean, what tends to be chaotic is 0 times infinity. So this is like just a way to remember it. But of course, we proved the claim that if both values are finite, then you can do the product.
But then we should write that the second term is not infinity, not that it's not 0.
Yes, you're right. Yes. Not infinity. Okay. Yes.
Sorry, I'm not sure. Well, I'm not sure. It's a fact that I'm not following. Why the Gm minus Gn has order minus 2 at P? So sorry. So you say that you are showing this by like based on the fact that Gm has order minus 2.
Yes. So this is something we proved in a previous
Okay, so it's a
previous
proof
session.
itself. Okay.
The effect about GM. I mean,
Uh-huh.
it was like let me just look for it.
Because I was not finding it, but if we already saw this, I will look for it later.
Yeah, it's essentially
Don't worry. I mean, I can look for it later.
so we had let me just remind you where to look for it. It's a bit, I mean, we proved something slightly different. We showed that Gn over X at O
Okay.
is n square, I think.
1 divided by
Yeah, 1
n squared.
divided by n square.
Okay, yes, this is familiar.
But what this means that Gn at O is like X over n squared. And X has degree 2, right? I mean, as a variable.
Yes.
So
Yes.
so it means that when you substitute O, I mean, O is like infinity comma infinity, and you substitute it instead of the X has like X is like infinity square.
I see. Okay.
So it means that Gn has order multiplicity 2 at O. And the same goes. We had another lemma for Gm, sorry, for Hn.
Yeah.
Right? We had like Hn
1 divided.
Y, I think it was 1 over m squared. So this implies
Cube.
at O, right? At O. So this implies that that the order of Hn at O is 3. Okay, because now Y has degree 3. Okay.
Yeah.
So basically, I mean, this is of course in O, but using the lemma, the translation lemma, this is what I mentioned earlier now, that using the translation lemma, we can deduce that the order of Gn at any other relevant point in En, for example, is also going to be -2.
Nice.
Okay.
Thank you. Make a lot of sense now. Thanks.
Okay, so going back to the proof, so this basically finishes the case we considered. I mean, we wanted to show that Gm minus Gn has order -2 at all these points that are in Em but not in En, and that is fine. We are able to express Gm minus Gn as u to the -2 for uniformizer at P, where the times some function that doesn't vanish and is not infinity. Okay.
Yes.
Okay. So the third case is the interesting and third case. These are points. Well, actually, there's like a case 2 prime. These are points in En, but not in Em. And this is a symmetric to case number 2. I mean, we don't care that, we don't care that M is bigger than N or N is, it doesn't matter for the analysis we did in case number 2. And then we have case 3, which are points not in En, say En, and not in En. And this case has 3 subcases. The first P in E M minus N and not in E N plus N. For this, then we have the following equation. We know that MP is equal to NP, but NP is not equal to minus NP. Right? Can you see this from basically we know that M minus N P is equal to O, and we know that M plus NP is not equal to O. So we conclude that MP is equal to NP, and NP is not equal to minus NP. And since we also know that P is not in EM union EN, we know that MP is not 0, is not O, and NP is not O. Okay, so one thing to notice is that GM minus GN at this point P is always going to be equal to 0. How do you see this? I mean, it's basically because we know that we know that MP is equal to NP. And so we want to determine the multiplicity of this 0. We also know that HNP is equal to HMP. Sorry, is not. Yeah, okay. We know that HNP is equal to HMP because of this, the green equality. Remember, Hn P is simply the y coordinate of the point n times p. And now we had a lemma about derivations. We calculated the derivation of Gm minus Gn in terms of Hn. This was 2 times m minus n times, well, sorry. This was 2m Hm minus 2n Hn. But we know that Hn and Hm are equal at P. So when we evaluate this derivation equation at P, we get 2m minus 2n times H, we choose one. Let's say Hm. Or let me even just take out the 2. So now we know that m minus n is prime to P, prime to the characteristic of the field. So and because MP is not equal to MP, sorry, to minus MP, P cannot be of order 2. But if P is not of order 2, then its y coordinate is different than 0. Sorry, MP cannot be of order 2. And this means that HMP is different than 0. But okay, so this really means that the derivation of Gm minus Gn at P is non-zero. So we conclude, what do we conclude? We conclude that Gm minus Gn has a 0 of order 1, also called simple 0. at P. Okay, remember that this derivation that we defined on rational functions, it has the properties that you know from derivations of polynomials, namely that if you have a root of a polynomial such that the derivation of the polynomial does not vanish at the root, then this root is of order 1. And if derivation vanishes n times, then and not n plus 1 times, then this root is of order n. Okay, so this proves the first subcase. Any questions about that? And now, do you follow?
I feel like I follow. I mean, so far things make sense.
But let's spin it completely. It's not hard. I can go over it again. It's maybe it's easier.
I mean, I think it makes sense. I mean, everything like matches. So, but I mean, yeah.
Lisa, what do you think?
I always forgoing over again. Please go again.
Okay, so we're saying we're in case number 3. These are points in EM but not in EN. Sorry, points that are neither in EM or in EN. And we take the first subcase, which is points that are in EM minus n, but not in EM plus n. For these points, we have the green equations. And the green equations translate to the other green equations with the double line. And we also know, of course, that that P does not belong to EM union EN. This is because we're like in case number 3. So this gives the two other green equations or inequalities. Now it's easy to check that GM minus GN evaluated at P is 0. Basically just by the assumptions. And also that Hn of P is equal to Hm of P. This is because of this specific equation. If MP is equal to NP, then the y coordinate has to be equal. So far, okay, Lisa?
Yes.
Okay, and now I'm saying we had we clearly have we know that P is a 0 of GM minus GN, and we want to compute the multiplicity of this 0. So it will be enough to show. I mean, I claim that the multiplicity is 1 here. And to prove this claim, it's enough to show that the derivation of GM minus GN at P is non-zero. You remember we had a theorem that says that the order of the derivation, I mean, basically the order of the derivation of R at P is the order of R at P minus 1. Right? This was like one of the things we proved about derivations.
Yes, but how we will know that the multiplicity is 1 if we prove that the derivation is non-zero? Because if the 0, it might be like 3.
No, I mean, the thing is, like, a function that doesn't vanish and doesn't, I mean, this derivation of gm minus gn is just another rational function,
Right.
which is always finite, in fact.
Right.
So if we prove that it's non-zero, then its order is 0, right? Because, I mean, a function that doesn't vanish, if we prove that it's non-zero at p, and we also know that it's not infinity at p, then it doesn't have a 0 or a pole at p. So the order of
Right.
this function at p is 0. But if the order of this function at p is 0, if this is 0, then I know
Oh, I
that
got it.
that order of r at p is 1. Okay?
Okay.
So it's enough to show that the derivation of gm minus gn at p is non-zero. But that's very easy, because I use this calculation about derivations, which expresses the derivation of gm minus gn in terms of hn and hm. But in our case, hm is equal to hn. So when I evaluated p, I get this expression. And this expression, I know, is not 0, and also not infinity at p, because m minus n is assumed to be prime to p, and hm of p is assumed to be non-zero. This is because m is not a point of order 2. The reason m is not a point of order 2 is because mp is not equal to n to minus mp. This is one of the assumptions. Okay, so all in all, we know that the derivation of gm minus gn at p is non-zero, and not infinity. So we get that it has a simple 0 there.
Okay. Sounds good.
Nicholas, are you following?
Yes, sorry, I was on my cell phone. Yeah, I'm following. I think on the high level, yeah. The details is get sometimes, but the last explanation that you already did was clear. Thanks.
Okay, great. Yeah, that's the main issue. I think the heart of the matter in this subcase, and also it's going to be in the other two subcases, is we use these properties of derivations in order to calculate the order of a rational function at a point. This comes in handy. It's kind of a useful piece of theory. So let's take a break, and we come back to the other two subcases. Okay, let's go back to it. And what are the other two subcases? The second subcase is that P is in EM plus N, but not in EM minus N. And this is symmetric. To case number one, subcase. Because if you go over the argument in subcase number one, you see that we didn't use anywhere well, it's just symmetric. I mean, you can do the derivation of Gn minus Gn at this P, and you get the same. So we are left with the third subcase, which means that P is not in M plus N. Wait, sorry. P is in the intersection E M plus N and EM minus N. And remember, we also assume that P is not in the union of EM and EN. So what equations can we conclude from these assumptions? We have MP is equal to minus NP. This is because P is in in EM or E of M minus N. We have MP is equal to NP. And we know also that MP is not O and NP is not O. And from this we conclude that 2MP is equal to NP, which is equal to O. Right? I can add these two equations. I guess I need to transfer one of them. This, if I add it like this. Yeah. Yeah, I can either add these two equations as they are, and then I get 2MP equal to O, or I could swap sides or subtract one equation from the other, and then I get the 2NP is equal to O. Now we know from the previous case that if I take the derivation of gm minus gn at p, well, here it's going to be 0. The reason is, I mean, I can express it as, let's see, 2m hm minus 2n hn at p. But I know that 2mp is equal to 2np, so they have the same y coordinate, and therefore this this expression vanishes. So far, it's okay.
Can you say again, like this last thing, like it vanishes because 2mp. Oh, okay, yeah, okay, sorry, I see.
Yeah, I mean,
Sorry.
yeah, I mean, I'm just saying like 2mp as points on the curve, 2mp is equal to 2np, and
Yes.
if you multiply by hm, it just means you take the y coordinate. So if the points are equal, they have the same y coordinate.
Yeah, totally. Thank you.
And okay, so we know, I mean, okay, we know that for the points p in this third subcase, gm minus gn at p is equal to 0, right? Because mp is equal to np, so they have also in particular the same x coordinate. And so we know that p is a 0 of gm minus gn, and it is of order bigger than 1 because the derivation does not vanish. And I want to show that it has in fact order 2. I mean, we know that the multiplicity is at least 2 because the derivation also vanish. In order to really show that the multiplicity is exactly 2, I would need to take a look at the derivation of the derivation. Derivation of gm minus gn. But that's okay because we have a formula for the derivation of gm minus gn. This is this 2m. This is now d of 2m hm minus 2n hn. And I want to evaluate this at p. Now, we know this is another calculation we did when we talked about derivations, is that if I do the derivation of hn, I get n times 3gn squared plus a. And obviously the same goes to m, right? hn is m 3gn squared plus a. So now when I want to calculate the double derivation, I need to do the derivation of this 2mhm minus 2nhn. But the derivation of a difference is the difference of derivations. So I get that this is now 2m squared 3gm plus a minus 2n squared g n squared, sorry, 3g n squared plus a. Okay, so now I substitute p, and since I know that 2np is equal to 0, it means that np is a point of order 2, which means that it's of the form omega comma 0 for omega a root of x squared plus 8x plus 1. Okay, so in particular, sorry, np is a point of order 2. It means that np is omega comma 0 for some omega. And now when I substitute np into this equation, I get the derivation of the derivation of gm minus gn evaluated at p is simply, I mean, here I have gm square, and when I do it to p, it's like it's taking the x coordinate of mp and raising it to the power of 2. So I simply get 2m squared 3 omega squared plus a minus 2n squared 3 omega squared plus a, which is the same as saying 3 omega squared plus a 2 and minus n plus n. Right, this last part is simply m squared minus n squared. Okay, and now this is non-zero because we assume that m plus n and m minus n are prime to p. This is So in order to show that the double derivation of gm minus gn at p is non-zero, it's enough to say why this factor is non-zero. Any idea why this factor should be non-zero?
Because omega is non-zero.
Omega is non-zero, but maybe 3 omega square is equal to minus a.
But it can't be equal to something with sign minus because omega square will be positive and multiplied by 3 will be positive.
Yes, but a is just a general coefficient. It could be minus. Could be
But
minus.
3 omega square can't be with sign minus.
Okay, but then maybe a is. I mean, the 3 omega square is positive. Let's say again, you need to think of omega in a finite field, so it's not exactly negative or positive, right? But even if it's just real numbers, okay, 3 omega square would be always positive, but it could be that a is negative. A is just a general coefficient of the curve, right? You have y square equals x. Sorry. Yeah, here it's x cubed. X cubed plus ax plus b. Right? Just this is a general coefficients. But there is something else. This we talked about it. So omega. Why did I write it? I should have written x cubed. Omega is a root of Sx, right? But we know that it cannot be a double root. Do you remember why?
No, I don't remember.
So elliptic curve generally does not have multiple roots of this polynomial.
Ah, right.
Okay, so this means that if I take the derivation of s, namely 3x squared plus a, and I substitute omega, I get something that is non-zero. This is equivalent to say that omega, if I know that omega is a root, if I want to say that it is not a double root or of any other multiplicity, then it's enough to say that the derivation of the polynomial at omega is non-zero. It's equivalent, in fact.
Okay.
So, okay, so I know that 3 omega square plus a is non-zero. It's basically because omega is not a double root, or because omega is a simple root. Of S. Okay, this, by the way, to say that omega is a simple root of S, it was equivalent to say that E is smooth. This was kind of the idea behind this property. Okay, so all in all, I get that the double derivation of gm minus gn at p is non-zero. And this means that the order of P at Gn minus Gn is exactly 2. Well, yes, it's exactly 2. Okay, and this fits our case. I mean, remember our subcase. Where are we? Yeah, our subcase is P is in em plus n and also in em minus n, but not in the other two, not in em and not in en. So when I take the coefficients in the divisor in the main statement of the theorem, I get 1 plus 1, which is 2. So I showed that if I take the order of Gm minus Gn, I also get 2. And this basically completes the proof.
I'm curious, should we somehow take care of infinity? Or is just somewhere outside of all cases and we don't care about it?
No, we took care about the point at infinity. This, let me remind you.
Oh, we just never mind. We just have point at infinity. We don't have separately 0 and infinity.
Yeah,
Yes.
yeah. I mean, this was in the first case. Points which are both in em and in en, they cannot be in em plus n, and they cannot be in em minus n. And O is one of these points, and we showed that the order of Gm minus Gn at O is minus 2.
Yes, that's right.
Okay. Now, how do you feel about the proof?
So this last part was cool. Thank you. The thing that I'm not, I mean, I'm just going again over the notes, but so we have the case 1 concludes that the order is minus 2. Case 2 concludes that the order is minus 2. But then case 3 concludes that the order is 2. Is this last sentence correct?
Case 3 has 3 subcases.
Right. I was mixing.
Yeah. So, I mean, in case 3, we take points that are not in em and not in en. So, in this divisor in blue.
Yes. So
In
it's
this divisor in blue, we take points that are here, maybe here.
yes, it's 1, and the subcase 2 is also order 1, and then
So
the last. Okay.
They could appear either in both of em plus n and em minus n, or just in one of them, but they definitely do not appear here. This is case 3.
Yes.
And you see, you divide it into subcases. In the subcase in which the points are in em plus n and in em minus n, this is actually the third subcase, then the coefficient should be 1 plus 1, so 2. We need to show that the order of Gm minus Gn at these points is 2. But if the point belongs to em plus n, but doesn't belong to em minus n, then we need to show that the order of Gm minus Gn is 1.
Yeah.
Okay. And if it's in and this is what we showed, and if it's in em minus n but not in em plus n, it's symmetric.
Yeah.
Okay.
Yeah.
So
Yeah. Good.
this covers
Thank you.
all the three subcases.
Thank you very much.
Okay. So, Nicholas, do you have questions about the proof? Okay. So corollary. I take the degrees. Yes. Okay. I now take the degrees. So I know, remember, I have divisor of gm minus gn is equal to the divisor generated by em plus n plus the divisor generated by em minus n minus 2 the divisor generated by en minus 2 the divisor generated by en. So taking degrees, let dk be the number of points in en. Taking degrees of this equation, we get 0. I mean, the degree of a principal divisor is always 0. And what is the degree of the divisor on the right hand side? You simply, this is dm plus n. I mean, the degree of this divisor is just you sum m plus n. I mean, sorry, you sum once the number of points in em plus n. So this is dm plus n plus dm minus n minus 2 dm minus 2 dm. Okay, this is an important formula. And now we okay, so we can already see if I take dk to be k squared, well, this satisfies the formula star. Why? I mean, I want to show that m plus n squared plus m minus n squared minus 2m squared minus 2n squared is equal to 0. But that's indeed the case, right? Here, this is like m squared plus 2mn plus n squared, and here it's n squared minus 2mn plus n squared, and this cancels with this, and these guys cancel with these guys. Okay, so dk equals k squared satisfy the recursive formula. And what I claim is that we can show that that's the only solution for the recursive formula. So this is kind of another piece of theory that we're going to use in how to solve recursive relations, namely linear recursive relations. Yes.
I'm not sure I understand. Why do you call it recursive relations?
Well, I mean, we know what is D1. D1 is 1, right? This has to be D1 is the number of points that are in E1. There is only one such point, namely O.
Yes.
D2 is 4.
Ah, you mean that? Okay.
Okay, and then you move. You could basically, hypothetically, you could calculate all the other D's, right? You have a recursion. Now here, I want to simplify. This is a recursion relation with like two indices, this m and n, and I want to simplify it. So I can take n equals 1. And I get d m plus 1 plus d m minus 1 minus 2d m minus 2, right? Because d1 is 2, d1 is 1. And now this is maybe more familiar as a recursive relation, right?
Right.
So it's enough to show that I only have one solution to the second. Let's call it double stack. Or actually, I think in the notes I called it RM. Okay, this is some relation between the various Ds, and enough to show that dk equals k squared is the only solution for Rm. Now, the issue here is I don't want to get into the whole theory of solving linear recursive relations. It's not hard. And in the notes, you have a reference for a book that does the complete treatment. But basically, in the theory, you distinguish between two cases. One in which it's called a homogeneous linear recurrence relation. It means that you don't have a free coefficient. And the other one is the inhomogeneous case in which you have a free coefficient. But the homogeneous case is easier to solve, and so usually you reduce the non-homogeneous case to the homogeneous case. And the way you do it is as follows. So let's call it a is a solution of Rn, and if Bk and is also a solution, then k squared minus bk as a sequence is a solution for the homogeneous relation. I call it RHN, which is a 0 equals dn plus 1 plus dn minus 1 minus 2 dn, and without the minus 2. Right? Can you all see this? I mean, if I have two solutions for the non-homogeneous recurrence relation. I subtract the two solutions, and since both of them are solutions to these equations, when I subtract these two equations, the free coefficient falls. Is this clear? Should I mean, just imagine dn plus 1 plus dn minus 1 minus 2 dn minus 2. And also for another guy, d prime m plus 1 plus dn minus 1 prime minus 2 d prime m minus 2. And both of these are equal to 0. Then I subtract the equations, and I get that dn plus 1 minus d prime m plus 1 plus dm minus 1 minus d prime m minus 1 minus 2 dm minus d prime m is equal to 0. Okay, so the difference, dm minus d prime m is a solution to the homogeneous linear relation. I mean, the one that I obtain when I erase the free coefficient. Is this clear?
This is clear, but I don't understand how it relates to the sequence. Why we don't take just two solutions, but we want to take a sequence.
Well, because I want to show that eventually I want to show that dk equals k squared is the unique solution to Rm. Okay?
Yes.
It's about, so I really need to consider sequences as solutions. There, I mean, possibly there could be other sequences. I know that one sequence dk satisfies this relation. I know that this relation has to hold, right? Whatever,
Right.
yeah. And I'm saying, okay, so how do I prove uniqueness? I will eventually prove uniqueness of solution to the homogeneous relation. The homogeneous
Right.
relation is easier to handle, basically. You will soon see why. So okay, so I'm saying, let's suppose that I have two solutions to Okay. Thank you, Ruth, and sorry if it's hard to catch up.
Yeah, no worries. Thank you. Bye.
Okay, so I'm saying, let's suppose that we have two solutions for the non-homogeneous relation. One solution is definitely k squared. The other solution, I just call it bk, but I have to consider the sequence. You see, Lisa?
Yes, but why won't you consider a sequence from 1 to k? Why you want to consider it to infinity?
Because this relation has to hold for any m.
Including infinity.
No, I mean when I write infinity, it just means you have bk for every k. For every natural number k, you have bk.
Okay. Okay, makes sense.
Okay. Now do you follow? Do you? This is kind of a new area.
Yeah, completely new for me. Like these concepts of like sequences and the thing that you are doing, it's fully new. So I'm not fully following.
Okay, so
But
let me
don't.
explain. It's very easy. I mean, when
Okay.
I write a bk like this, I just mean b1, b2, b3, and so on up to bk, and then you continue. It's like an infinite. It's like an infinite sequence. Okay, it could be. I mean, the sequence ak, a equals 1 to infinity. This is equal to 1, 4, 9, and so on. Right? This is one particular sequence that we know that satisfies the non-homogeneous
Okay.
relation, right?
Thanks for the example with numbers.
Okay, and now so I'm saying if I had another sequence bk, this is bk, then I know that the difference of the sequences, namely k squared, it's the difference of the sequences is simply the sequence in which you take the difference in each coordinate, right? So this is like ak minus bk. The difference of the sequence is another sequence, and this other sequence would have to satisfy the homogeneous, sorry, the non-homogeneous relation. Sorry, it would have to satisfy the homogeneous relation, right? This is what I did here. Here in this part, I showed that if you take a sequence, let's say dm, that satisfies the non-homogeneous relation, and you take another sequence, d prime m, that also satisfy the non-homogeneous relation, and you subtract the two sequences, then the resulting sequence satisfies the homogeneous relation. Is this clear or no?
Yes, I think. Yeah. Thanks.
I mean, what I'm saying is, so k, I'm saying that k squared minus bk, whatever bk is, satisfies the relation RHM. Okay, and now I'm going to show that the relation RHM, I actually know how to solve it. So the characteristic or you know what, let me just because we're running out of time, I'll state a lemma that we can prove next time. All solutions to RHM are of the form let's call it AK. AK is equal to alpha 1 plus alpha 2. Okay, and let's just assume this lemma. It's very easy to prove. If I assume this lemma, then I know that k squared minus bk needs to be equal to alpha 1 plus alpha 2 k for all k. For some alpha 1 and alpha 2 that I don't know, but I don't need to know. There are some real numbers. But I have two instances. I know that for k equals 1, bk has to be 1. And for k equals 2, bk has to be 4. So I get that 1 minus bk is equal to alpha 1 plus alpha 2. No, I get that, sorry, that 1 minus 1 is equal to alpha 1 plus alpha 2. And I also get that 4 minus 4 is equal to alpha 1 plus 2 alpha 2. But this system of equations has only a unique solution, which is alpha 1 equals alpha 2 equals 0. So I get that a k squared minus bk is equal to 0 for all k, i.e. bk is equal to k. If bk is equal to k squared. Okay? So modulo the lemma, we proved that dk equals k squared is a unique solution. Okay, is this more or less clear? I mean, we will have to save the proof of the lemma and another small issue for next time.
Yeah, looks good.
Okay, so you see, just take a look at the variety of tools we did here. I mean, we eventually want to show that En is going to be isomorphic to Zn times Zn. And
All right, we
yeah,
started here.
This was the beginning of the whole thing. What we basically did now is showing that En, the number of points in En is n squared. In order to prove this part, we did a theory of derivations. Using the derivations, we were able to calculate the divisor of GM minus GN. And then we got a recurrence relation. This is kind of linear algebra stuff. We showed, let's say, modulo dilemma, that the recurrence relation has a unique solution, and this is n squared. So we used at least derivations and recurrence relations. And then for the last part, this we do next time, I'm simply going to use the classification of finite abelian groups. So this is like a very wide set of tools, all meant to prove this this result. All right, questions before we end up?
It's not a question, but I met someone who told me that they were watching all the lectures that are currently published on YouTube, and they were really sad that the lectures stopped being uploading. I thought that maybe as far as we are still recording them, maybe there is some way to upload them if someone was upset about that.
Yeah, definitely. It's I will do it. It's just that I was waiting to collect some other recordings and then upload all of it together.
Yeah, it makes sense.
So yeah, you can tell this person that it's going to be up sometime soon, the next couple of months, I think.
Yeah, that's what I said. That I think they will be uploaded, but just a bit later.
Yeah. All right. Anything else? Then have a nice weekend.
Thank you very
You too.
much.
Yeah.
Have a nice weekend. Bye.